Imagine a place in space so empty that if our entire galaxy were inside it, you would see absolutely nothing. No stars, no light, just complete silence stretching in every direction. Elsewhere, pieces of iron are falling from the sky. A black hole waits at the center of a galaxy large enough to swallow our entire solar system without slowing down. Tonight, we explore the places in the universe that seem like they shouldn't exist. A void that challenges cosmology, a structure far too enormous to have formed naturally, and something pulling millions of galaxies toward a point we cannot even see. Prepare yourself. We begin. The boat is void. Imagine pointing a telescope at a random patch of sky and seeing nothing. Not a dim star, not a faint glow from a distant galaxy. Just darkness, stretching further than the human mind can comprehend. This is the Boötes void, a spherical region of space, about 700 million light-years from Earth, spanning roughly 330 million light-years across. To put that in perspective, the entire Milky Way is only about 100,000 light-years wide. The Boötes void could contain 3,000 galaxies like ours, lined up end to end, and still have space to spare. Here's where it gets strange. Cosmologists model the formation of the universe over billions of years. Matter should gather along the cosmic web. Gravity pulls gas into filaments. Filaments collapse into galaxies. Galaxies cluster together, and empty regions form, but these voids are normally small, predictable, and expected. The Boötes void is not. By every known model of cosmic structure formation, a void this large shouldn't exist. Gravity alone would need roughly 100 billion years to create an emptiness of this scale. The universe is only 13.8 billion years old. The math doesn't add up. This is a verified measurement and remains one of modern cosmology's most unsettling questions. One theory suggests the Boötes void formed when several smaller voids merged over time, creating one vast emptiness larger than any single region should produce. This idea is plausible but still doesn't fully explain its size. Another, less official idea is that the void hints at physics we do not yet understand, forces acting across vast scales, structures hidden beneath the known universe itself. A fascinating detail: in 1981, astronomer Robert Kirshner and his team discovered this void almost by accident while mapping galaxy positions. They expected to find galaxies, but instead found an enormous hole in the universe. When published, many scientists doubted it. The void was so large that some assumed the data must be wrong. It wasn't. Inside the Boötes void, astronomers have identified roughly 60 galaxies. Statistically, that area should contain about 2. So, where did the other 940 go? The answer remains unknown. If you stood on a planet inside the Boötes void, the sky would appear almost empty. No nearby galaxies, no lights, no cosmic neighbors in any direction. You would experience a loneliness unlike anything on Earth. The void itself seems to stare back, reminding us that the universe has gaps that make our existence feel like a tiny island in an endless sea. Some objects in the universe are so extreme that if you were near them, the atoms in your body would stretch and deform. Every molecule would be rearranged, and survival would be impossible. This is confirmed by physics, not speculation. One of the most powerful objects ever measured is a magnetar known as SGR 1806-20. In December 2004, it released a burst of gamma rays and X-rays so intense that, despite being 50,000 light-years away on the far side of the Milky Way, the energy pulse ionized Earth's upper atmosphere. Instruments around the world detected the event, and satellites temporarily saturated their sensors. From 50,000 light-years away, a single flash affected our planet. Magnetars form like regular neutron stars through the collapse of a massive star's core, but the exact conditions that generate such extreme magnetic fields are still under study. One leading theory suggests that the rapidly spinning core of a collapsing star produces a dynamo effect, amplifying the magnetic field to extraordinary levels within the first seconds of the star's death. Magnetars are unstable. Their solid crust is under constant stress from the twisting magnetic field, and periodically it cracks, producing starquakes that release enormous amounts of energy in milliseconds. The 2004 gamma ray burst from SGR 1806-20 was triggered by one of these crust fractures. A similar event scaled to Earth's mass would be enough to destroy the planet entirely. Currently, around 30 magnetars are confirmed, though many more likely exist, either undetected or faded, over roughly 10,000 years. They gradually lose their extreme magnetic energy, becoming more typical neutron stars. For that brief window, magnetars are among the most energetically violent objects known, releasing more energy in a fraction of a second than our sun produces in hundreds of thousands of years. Now imagine a star that does not explode, does not spin wildly, and does not erupt. A star that simply cools and hardens into a state physics says shouldn't exist at these temperatures. Stars are typically balls of plasma, hot, turbulent, and gaseous. But the neutron star RxJ 1856, Wu Dao San Ti Bai Wu Shi, located about 400 light-years from Earth and discovered in the 1990s, behaves differently. Its surface acts like a solid, possibly a crystalline neutron matter crust, or a dense, rigid quark-like surface. Unlike plasma, observations show it is more compact than any neutron star model predicts. One explanation is that its interior consists of exotic quark matter, where quarks are no longer bound in protons and neutrons, but exist in a free, dense state. If true, this is not technically a neutron star, but a quark star, a type of object never definitively confirmed. Its surface temperature is around 400 degrees, leftover from the original stellar explosion. And unlike typical neutron stars, it is eerily quiet, radiating steadily without pulses or eruptions, like a glowing crystal in space. If imagining a solid star is challenging, consider a black hole so massive that conventional measures lose meaning. 618, located about 4 billion light-years away. It powers one of the brightest quasars ever observed. Its mass is 66 billion times that of the Sun, far exceeding typical supermassive black holes. Its event horizon spans roughly 60 billion miles, 18 times the width of our solar system, so every planet, moon, and asteroid could fit inside with room to spare. The gravity at the horizon is surprisingly gentle, but once crossed, all paths lead inward. Its gravitational influence extends hundreds of thousands of light-years, subtly affecting surrounding galaxies, and it consumed enough material to amass 66 billion solar masses early in the universe's history. Space is not just empty, it contains objects whose scale defies comprehension. Not all extremes are massive objects. Some are extreme weather phenomena. On the exoplanet WASP 76b, iron literally rains from the sky. The planet is tidally locked, meaning one side always faces its star. The day side reaches 400 degrees, vaporizing iron into gas, which is carried by winds exceeding 18,000 miles per hour to the night side, where it condenses and falls again as iron rain. This cycle of vaporization, wind transport, condensation, and precipitation is continuous, a form of metal weather. Another extreme world is 55 Cancri E, a super-Earth about 41 light-years away. Its host star is rich in carbon, possibly resulting in an interior dominated by diamond under extreme pressure. Surface temperatures exceed 20 degrees, with potential volcanic activity erupting carbon compounds instead of silicate rock. Some exoplanets, like GJ 1214b, are water worlds with oceans so deep that their behavior has no Earth equivalent. These examples show the universe runs billions of experiments simultaneously, creating planets with metal rain, diamond cores, and oceans without a flaw. Some objects, like magnetars or quark stars, defy physics as we know it. Others, like supermassive black holes, dominate space on unimaginable scales. And planets like WASP 7, 6b, or 55 Cancri e reveal that even weather and geology can operate under rules far beyond anything on Earth. The cosmos is vast, violent, strange, and endlessly fascinating, offering extremes that challenge our understanding and invite us to continue exploring its mysteries. GJ 1214 b is located roughly 42 light-years from Earth and was confirmed by researchers in 2009 using ground-based telescopes. It is classified as a mini-Neptune, smaller than the ice giants of our solar system, but significantly larger than Earth, with a diameter about 2.5 times that of our planet. What makes it unusual is its low density. Compared to its size, the planet is not very massive, which rules out a rocky interior. Combined with radius and mass measurements, the evidence strongly suggests an interior dominated by water, but not water as we know it. At the extreme pressures deep inside a planet this size, water behaves in exotic ways. Near the surface, it may exist as a familiar liquid or gas, but descending deeper, it is compressed into phases that are alien to our experience. Researchers call these forms Ice 7, Ice X, and subaryonic water, in which water molecules lock into strange lattice structures, or where oxygen atoms form a solid crystal while hydrogen atoms move through it like a fluid. These phases have been produced briefly in laboratories under extreme conditions, but never persist naturally on Earth for more than fractions of a second. On GJ Ezerkate, they make up the bulk of the planet. Descending from the upper atmosphere, one would pass through a thick, hot, steamy layer, then into a crushing, bottomless ocean, and then into water phases that grow progressively stranger, harder, and less recognizable, ultimately reaching pressures and temperatures at the core that science can model but cannot fully test. There is no continent, no island, no reef, no rock or canyon. The planet is a seamless, layered sphere of water in states humans cannot hold in their hands. Its thick, cloudy atmosphere blocks attempts to measure composition directly, with clouds potentially made of zinc sulfide or potassium chloride, forming under temperatures of several hundred degrees. A scorching, cloud-covered, bottomless ocean world. GJ 1214 b highlights the strangeness of exoplanets compared to the solid ground we rely on Earth, showing a reality beyond the limits of human architecture, biology, and instinct. Yet some discoveries challenge not just a single world but the structure of the entire observable universe. Modern cosmology assumes the universe has no preferred direction, a principle called the cosmological principle on large scales. Matter and energy are distributed uniformly, with no center, no edge, no axis. But the so-called axis of evil challenges that assumption. When the Wilkinson microwave anisotropy probe, and later the Planck telescope, mapped the cosmic microwave background in detail, they found the largest scale temperature fluctuations aligned along a consistent direction across the sky, suspiciously close to the plane of our solar system and the direction of the equinoxes, confirmed by two independent missions using different instruments and methods. This alignment is statistically improbable in a truly random universe. Possible explanations include instrumental error, local foreground effects, or the radical idea that the universe genuinely has a preferred direction, implying an asymmetry dating back to the Big Bang. The axis of evil is an anomaly confirmed by data but unexplained, suggesting that space itself may possess a subtle orientation. Meanwhile, some objects erupt with rhythm and precision. Quasi-periodic eruptions are sudden, intense bursts of X-ray energy from regions just outside central black holes in certain galaxies. They repeat at intervals from roughly 1 to several hours. The first confirmed system exhibiting this behavior was GSN 069, about 250 million light-years away. Its central black hole, around 400, 0.000 solar masses emitted X-ray pulses every 9 hours, each lasting about an hour. Later, the pattern quieted for years before resuming, suggesting a repeating process. One explanation is a repeating partial tidal disruption event, in which a star in a close orbit is partially stripped of material during each approach, producing the bursts. Another possibility is a smaller compact object disturbing the black hole's accretion disk. Both mechanisms are plausible, and the phenomenon allows astronomers to observe galactic cores pulsing on timescales measurable within a human lifetime. A rare opportunity in a universe where most events unfold over millions or billions of years. These violent cosmic processes are responsible for every heavy element humans have ever touched. While hydrogen and helium formed in the Big Bang, and elements up to iron were forged in massive stars, heavier elements like gold, platinum, and uranium required far more extreme conditions. In August, Dawami Szaptasplezece, gravitational wave observatories in the US and Italy detected a signal from the collision of two neutron stars, 130 million light-years away. Unlike black hole mergers, this event produced light in addition to gravitational waves. Telescopes worldwide observed a kilonova, confirming that such collisions generate vast quantities of heavy elements, including enough gold and platinum to equal 40 to 100 Earth masses in a single event. This rapid neutron capture process occurs in extreme neutron densities, creating the heaviest elements in fractions of a second and seeding future star systems, planets, and life. Every gold ring, silver necklace, and uranium atom on Earth originated from such catastrophic events. Some stars are ejected entirely from galaxies, becoming hypervelocity stars moving at over 3 million mph. Unable to return to their home galaxy, these stars may carry planets with them into intergalactic space, perpetually illuminated by their star but isolated from everything else, traveling alone for billions of years in darkness. The study of these stars provides insight into the mass of the Milky Way and the dynamics near Sagittarius A*, the supermassive black hole at our galaxy's center. When binary star systems venture too close, tidal forces can capture one star while flinging the other outward at tremendous speed, a process called the Hill's mechanism. Finally, the limits of what we can observe are defined by the cosmological horizon, a boundary created by the expansion of space itself. Unlike a common misconception, galaxies are not moving through space. Space itself is stretching, carrying galaxies along like raisins in rising dough. The observable universe extends roughly 46 billion light-years in all directions, despite the universe being only 8 billion years old, because space has expanded during that time. This expansion is accelerating, confirmed by observations of distant supernovae in 1998, fundamentally affecting how we perceive the ultimate limits of the cosmos. Dark energy, which makes up roughly 68% of the universe's total energy content, is driving the accelerating expansion of space. Because of this, some galaxies we currently observe are moving away from us faster than the speed of light, not because they are traveling through space at impossible velocities, which physics forbids, but because space itself is expanding so rapidly that the distance between us and those galaxies grows by more than 1 light-year per year. Light emitted from those galaxies in the past can still reach us, but any new light leaving them now will never arrive. Over time, as this expansion accelerates, more and more galaxies will cross our cosmological horizon, their light redshifting into invisibility. Billions of years from now, any observers remaining in our galaxy would see a sky dramatically emptier than ours, not because galaxies were destroyed, but because the universe carried them beyond the limits of detection. We exist at a moment in cosmic history before this horizon swallows everything. The edge of what we can ever know is already moving outward, and beyond it lies information we can never confirm. The universe may hold even stranger objects. The Big Bang may have produced not only matter and energy, but also primordial black holes formed not from dying stars, but from the extreme density fluctuations in the first fractions of a second after the Big Bang. In regions where density was high enough, Gravity caused an immediate collapse, creating black holes ranging in mass from that of a mountain compressed to a single atom, to millions of solar masses. These primordial black holes drift through space, interacting gravitationally but emitting no light, no radiation, entirely silent. Some researchers propose that these ancient black holes could constitute a portion of dark matter, the invisible substance making up roughly 27% of the universe's mass energy. If so, some could exist in our galaxy right now, possibly even within our solar system, subtly influencing gravitational trajectories. Hypothetical searches for such objects include looking for microlensing events, brief brightening of distant stars as a black hole passes in front, but none have been confirmed yet. The possibility that remnants of the Big Bang still quietly inhabit our cosmic neighborhood is both unsettling and profound. Mathematical models of general relativity predict objects called white holes, mirror images of black holes, where matter and energy can only exit, never enter. Nothing has been observed, yet physics requires their possibility. Some theories connect black holes and white holes through wormholes, tunnels in space-time where matter falling into a black hole could emerge elsewhere. In loop quantum gravity, black holes may eventually bounce into white holes over enormous timescales. While speculative, these ideas highlight that the universe often behaves according to mathematics, even when we cannot observe it directly. The universe also contains structures so vast that their existence challenges our models. Gravity and the speed of light limit how large, coherent structures can form. Yet the Hercules Corona Borealis Great Wall, identified through clustering of gamma-ray bursts, spans roughly 10 billion light-years, about 25 times larger than expected. If confirmed, such structures defy the cosmological principle, which assumes no preferred directions and uniformity on large scales. Quasars, the luminous cores of distant galaxies powered by supermassive black holes, illustrate the early universe's extreme activity. Some already shone brightly just a few 100 million years after the Big Bang, with black holes hundreds of millions or billions of times the mass of the Sun, growing far faster than standard physics predicts. Proposed solutions include massive seed black holes formed from direct collapse of gas clouds or periods of super-Eddington accretion. But the precise mechanisms remain uncertain. Some objects in our galaxy move independently of stars, planets, and galaxies. Rogue planets drift through interstellar space, cold and dark, without a star, orbit, or light. They may retain internal geothermal heat, and some could maintain subsurface oceans insulated beneath thick hydrogen atmospheres, potentially supporting life entirely independent of a star. Likewise, hypervelocity stars, ejected from the Milky Way at speeds exceeding 3 million mph via interactions with Sagittarius A*, travel alone through intergalactic space for billions of years, possibly carrying planets with them, forever isolated. The expansion of the universe itself imposes absolute limits. The cosmological horizon defines the observable universe, a boundary beyond which light will never reach us. Galaxies are not moving through space. Space itself is stretching, carrying galaxies along like raisins in rising dough. Currently, this horizon extends roughly 46 billion light-years. Even though the universe is only 8 billion years old, as expansion accelerates, dark energy will carry more galaxies beyond reach, and the observable universe will appear increasingly empty. Meanwhile, even within our own solar system and nearby space, exotic extremes exist. Titan, Saturn's largest moon, has liquid on its surface, it including rivers, lakes, and seas. But this liquid is methane and ethane, not water. At Osuta Shaptezeci Shinoadriktse, water is frozen solid, yet hydrocarbons flow like liquids, raining from clouds and replenishing these alien bodies. These examples, alongside rogue planets and mini-Neptunes like GJ 1214b with oceans of superionic water, demonstrate that the universe continuously produces environments utterly alien to human experience, challenging every assumption about matter, chemistry, and habitability. Titan, Saturn's largest moon, contains the largest confirmed sea in the solar system, Cracca Mare, covering roughly the same area as the Caspian Sea on Earth. It is filled with liquid methane, so cold that oxygen gas, if released there, would instantly freeze as frost. The shoreline is carved not by water waves but by methane tides, pulled by Saturn's gravity. The seafloor is likely coated in organic sediments, complex carbon compounds that have accumulated over billions of years. Titan's thick, nitrogen-rich atmosphere, laced with organic chemistry, interacts with ultraviolet light from the sun. Methane molecules in the upper atmosphere break apart, creating a haze of complex organics called tholins. These tholins drift down, accumulating on the surface and potentially dissolving into the hydrocarbon seas. Similar chemical processes may have occurred on early Earth, where simple molecules in liquid environments gradually formed complex structures, ultimately paving the way for life. Titan represents a frozen extreme of this process. While the energetics of methane-based chemistry differ from water-based life, the universe repeatedly demonstrates that wherever chemistry cycles in a liquid medium, complexity tends to emerge. NASA's Dragonfly mission, scheduled to arrive in 2027, will directly explore Titan's chemistry, flying through the thick atmosphere and landing at multiple sites to sample the hydrocarbon-rich environment. For the first time, humanity will directly ask, is there chemistry here? Unlike anything we have seen before, Venus, in stark contrast, operates by extreme heat rather than cold. Similar in size and mass to Earth and located at roughly the same distance from the Sun, Venus should be temperate. Instead, its surface temperature reaches approximately 465 degrees Celsius, hotter than Mercury, and enough to melt lead. Its thick atmosphere, roughly 96% carbon dioxide, creates a runaway greenhouse effect, producing pressures about 92 times that at Earth's surface, equivalent to being 900 meters underwater. Spacecraft cannot survive more than about 2 hours on the surface. The Soviet Venera landers, sent between 1970 and 1982, returned images of flat rock slabs under an orange sky before succumbing to heat and pressure. The orange glow comes from dense sulfuric acid clouds above, reflecting sunlight and producing acid rain that evaporates before reaching the surface. At roughly 50 kilometers altitude, however, conditions are much milder pressure, comparable to Earth's surface. Temperatures around 30 degrees Celsius, trace water vapor, and chemical ingredients for potential reactions. In 2020, a study claimed the detection of phosphine in this layer, a gas on Earth produced almost exclusively by biological or industrial processes. Though detection remains debated, Venus's clouds remain one of the few places in the solar system where Earth-like chemistry could theoretically occur. Venus is a world of extremes, a surface instantly lethal to life below, and a cloud layer that could support chemical complexity above. Most of the universe, however, is invisible, not dark like space between stars, nor transparent like glass, but truly invisible. It does not emit, absorb, or interact with light. Dark matter accounts for roughly 27% of the universe's mass energy content. Its existence is confirmed through galaxy rotation curves, gravitational lensing, cosmic structure formation, and the cosmic microwave background. Every galaxy, including our own, sits within a dark matter halo, a roughly spherical distribution extending hundreds of thousands of light-years beyond visible stars. These halos contain smaller clumps, sub-halos, potentially passing through regions like our solar system. While no dark matter substructure has been directly observed, its gravitational effects may subtly influence planetary orbits. Candidates for dark matter include weakly interacting massive particles, axions, and possibly primordial black holes. All are actively tested, yet none confirmed, beyond dark matter. The universe may contain even stranger states of matter. Normal matter is built from atoms, which contain protons and neutrons, themselves made of up and down quarks bound by the strong nuclear force. Under extreme pressures, quarks may exist in a free state across an object. This quark-gluon plasma, briefly created in particle accelerators, could form permanently inside neutron stars. In certain conditions, some quarks may convert to strange quarks, forming strange quark matter, hypothesized to be extraordinarily stable. A neutron star undergoing this conversion would become a strange quark star, smaller and denser than a neutron star of the same mass, with a surface that is a direct boundary between exotic matter and vacuum. Candidate objects such as RxJ 1856, 5 to 3754, and PSRJ 95267 remain under study, with confirmation extremely difficult. Strange quark matter, if it exists, may propagate upon contact with ordinary matter, though such scenarios remain speculative. Even closer to home, dramatic phenomena have occurred in our galaxy recently. In 2010, NASA's Fermi Gamma Ray Space Telescope revealed two enormous lobes of high-energy gas and gamma radiation, extending roughly 25,000 light-years above and below the Milky Way's plane. These Fermi bubbles, visible only in gamma rays, are remnants of a past active phase of Sagittarius A*, our central black hole. Their sharp edges suggest a relatively young structure formed over millions of years, likely from energetic outflows as the black hole consumed surrounding material. These bubbles may also contribute to the high-energy cosmic rays constantly bombarding Earth. The galactic center is not just a gravitational anchor, it is a dynamic, occasionally violent engine shaping our galaxy and sending energy outward across tens of thousands of light-years. The Milky Way is shaped not only by gravity, but by energetic events that have left signatures across millions of years. The Fermi bubbles are the clearest evidence of this enormous lobes of high-energy gas and gamma radiation, extending roughly 25,000 light-years above and below the galactic plane. They reveal the history of Sagittarius A*, our central black hole, and demonstrate that a single galaxy can carry structures on scales that dwarf anything else locally. If one galaxy can host such strange phenomena, it raises questions about the arrangement of entire groups of galaxies. Galaxies should spin independently. Angular momentum from the early universe was distributed essentially randomly, and no known physical mechanism should coordinate the spin directions of galaxies separated by millions or billions of light-years. Yet surveys of galaxy spin axes in large-scale structures reveal statistically significant alignments. In some supercluster filaments, spiral galaxies rotate in directions aligned with the filament, far more often than chance predicts. Quasars exhibit similar behavior in 2014. A study of over 19,000 quasars found their spin axes aligned with each other and with the cosmic structures surrounding them across distances of billions of light-years. No force or interaction could have coordinated these orientations since the Big Bang. These correlations may reflect conditions in the primordial universe, imprinting preferred directions into the distribution of angular momentum before galaxies even formed. Such patterns connect naturally to other anomalies like the axis of evil and the cosmic cold spot, suggesting that the universe at the largest scales may be far more structured and directional than standard models predict. Yet after all of these extreme phenomena, from the Botez void and the Great Attractor, to supermassive black holes like TON 618, to hypervelocity stars and neutron star collisions, everything ultimately trends toward one final fate. The universe ends quietly, in the most absolute, undetectable way possible in heat, death. The second law of thermodynamics dictates that entropy, the measure of disorder, always increases. Energy spreads. Concentrated sources like stars and black holes dissipate, and the universe as a closed system moves toward maximum entropy. This process is confirmed and inevitable under current physics. The timeline is unimaginably vast. The universe is approximately 14 billion years old. The last hydrogen-burning star will fade in roughly 100 trillion years. Afterward, the degenerate era begins, with brown dwarfs and white dwarfs cooling slowly over quadrillions of years. Eventually, all remaining matter collapses into black holes or drifts into the void. Even black holes themselves slowly evaporate through Hawking radiation, with TON 618 at 66 billion solar masses, persisting for a period so long it dwarfs every other timescale in cosmic history. When the final particles are emitted, the universe will contain nothing else, no structure, no temperature gradient, no concentrated energy. Time itself will cease to have meaning because no change occurs, nothing evolves, nothing moves, and no energy differential exists. In that ultimate stillness, the universe will retain no evidence of its extraordinary history. The Botez void, the great attractor, TON 618, the gold forged in neutron star collisions, the hypervelocity stars cast into intergalactic space, the massive 10 billion light-year structures, everything will dissolve into uniformity. The universe will keep its secrets completely. And yet, for this brief window between the beginning and the final stillness, stars burn, structures form, planets orbit, and galaxies rotate. In this fleeting interval, conscious beings may look up and ask where it all came from. That question, perhaps, is the most remarkable product of the cosmos, and it remains unanswered, a testament to the extraordinary complexity and mystery of the universe. The universe is far stranger than we usually imagine. From the colossal emptiness of the Botez void to the enormous gravitational pull of the great attractor. From hypervelocity stars traveling alone in the intergalactic void to planets where iron rains from the sky. The cosmos challenges everything we know about matter, energy, and life itself. Yet these are only part of the story. Each extreme phenomenon invites broader questions. How did matter organize itself into the cosmic web? What governs the growth of supermassive black holes? How do exotic phases of matter form under conditions we cannot reproduce on Earth? Ultimately, what is the fate of everything we observe? The expansion of the universe, accelerated by dark energy, is one of the most profound mysteries. Dark energy is measured to make up roughly 68% of the universe's total energy content, driving galaxies apart at ever-increasing speeds. Some galaxies are now receding faster than light, not by moving through space, but because space itself is stretching. This expansion introduces limits to observation. Galaxies crossing the cosmological horizon are lost to sight forever. Over billions of years, the night sky as seen from any galaxy will become increasingly empty, leaving observers in darkness, long before stars burn out completely. Yet space is not empty, invisible yet dominant. Dark matter makes up about 27% of the universe's mass energy, shaping galaxies and clusters, providing the scaffolding on which cosmic structures form. Its exact identity remains unknown. Candidates range from weakly interacting massive particles to axions, to primordial black holes, remnants of density fluctuations in the first fractions of a second after the Big Bang. These ancient objects, if they exist, could drift through our galaxy silently, affecting gravitational dynamics in subtle ways. Beyond dark matter, extreme conditions produce forms of matter even stranger, neutron stars, and potentially strange quark stars, compress quarks into exotic states that cannot exist naturally on Earth, under immense pressures. Up, down, and strange quarks may form a stable, dense lattice called strange quark matter, creating a star smaller, denser, and fundamentally different from an ordinary neutron star. Some pulsars, like the Black Widow pulsar, spin hundreds of times per second, consuming their companions to maintain extreme rotation. These objects emit radiation precise enough to rival atomic clocks, yet the physics underlying them is only partially understood. The early universe also produced the first black holes. While many arose from collapsing stars, primordial black holes could have formed from local density fluctuations during the Big Bang, creating objects ranging from microscopic to millions of solar masses, distributed throughout space since the earliest moments. These relics may explain part of the dark matter content and remain an active focus of observational research. From gravitational lensing to subtle orbital perturbations in the outer solar system, the large-scale structure of the universe is astonishing. Galaxies align along filaments of the cosmic web, interspersed with enormous voids like the Botez void. Observations show surprising correlations in galaxy spin axes across billions of light-years, hinting at primordial patterns imprinted in the universe's first moments. Similarly, anomalies such as the axis of evil and the cold spot in the cosmic microwave background suggest large-scale anisotropies that challenge standard cosmology. Are these phenomena independent, or evidence of a deeper, unseen order? The question remains unresolved, highlighting how much we still do not understand about the universe's architecture. Extreme environments exist even within planets and moons. On Titan, Kraken Mare contains vast seas of liquid methane, with organic tholins falling from the atmosphere, producing a frozen analogue of prebiotic chemistry on early Earth. Venus offers the opposite extreme surface temperatures above 460 degrees Celsius, crushing pressures and clouds of sulfuric acid, yet at altitudes of 50 kilometers. Conditions are surprisingly temperate, raising questions about potential chemical activity or even microbial habitability. Exoplanets extend this variety to extremes. We could scarcely imagine super-Earths with diamond interiors, ultra-hot Jupiter's raining molten metals, and water worlds with high-pressure exotic phases like superionic or ice-X water. Even on the scale of galaxies, quasars provide extreme laboratories, powered by supermassive black holes millions or billions of times the mass of the Sun. Quasars in the early universe emitted more energy than their host galaxies combined, challenging models of black hole growth under the constraints of the Eddington limit. Some of these black holes grew faster than theory predicts, suggesting new physics, unusual initial conditions, or super Eddington accretion may have been at work. The universe is dynamic, is violent, and yet elegant. Hypervelocity stars are flung from galaxies at millions of miles per hour, potentially carrying planets into intergalactic space. Isolated in darkness for billions of years, even rogue planets drifting without stars may retain subsurface oceans heated by radioactive decay, offering theoretical niches for life entirely independent of stellar energy. Ultimately, all phenomena lead to the same end. Entropy will increase, energy will spread, stars will burn out, black holes will evaporate, and galaxies will drift beyond our horizon. The universe approaches heat death, a state of maximum entropy, where all energy is uniformly distributed, and no processes are possible. Time itself becomes meaningless because nothing changes. Yet in the brief cosmic window we inhabit, stars shine, galaxies rotate, planets orbit, and life arises. For this fleeting moment, the universe allows consciousness to emerge, to observe, and to wonder at the mysteries we may never fully comprehend. Science continues to probe these extremes, from particle accelerators creating quark-gluon plasma to telescopes detecting distant gamma-ray bursts, from spacecraft exploring Titan's seas to modeling the effects of dark energy on the universe's fate. Each discovery deepens our understanding while reminding us of how little we truly know. The universe is stranger, more structured, and more dynamic than we ever imagined. And even in its quietest reaches, it holds secrets that challenge every assumption we have about space, matter, energy, and life itself. Space and time are not two separate entities. They merge into a connected entity known as the space-time continuum. Every event in the universe occurs within the context of space-time, and objects, energy, or gravitational fields all have the ability to bend or distort it. Extreme phenomena such as black holes, white holes, or extremely fast pulsars are living evidence of this maximum curvature, where ordinary physics becomes almost powerless, and the laws we are familiar with remain only approximations. According to Einstein's general theory of relativity, the density of matter and energy determines the degree of curvature of spacetime. When they concentrate to an extreme degree, such as at the center of a black hole, they create a gravitational singularity, a singular point where density becomes infinite and current physics no longer applies. These singularities remain one of the greatest mysteries of the universe because they mark the boundary between current physical knowledge and what cannot yet be explained. In addition, the expansion of spacetime driven by dark energy also raises major questions. As the universe expands at an accelerating rate, spacetime stretches to the point where distant galactic structures become so separated that light can no longer travel from one region to another, creating extreme observational limits such as the cosmic horizon. In the Big Rip scenario, spacetime itself would expand to such an extent that it would break apart the bonds of all matter, from galaxies down to subatomic particles. An important scientific challenge today is that general relativity has not yet been perfectly unified with quantum mechanics. We still do not have a complete theory capable of describing physics at singularities, extremely fast pulsars, or in conditions of extreme gravity and density. These studies are not only crucial for understanding how the universe operates, but also open the door to exploring theoretical phenomena such as primordial black holes, quark stars, and white holes, extreme objects that we currently understand only partially through indirect observational methods. Understanding spacetime, how it bends and responds to matter and energy, is the first step toward delving deeper into the mysteries of dark matter and dark energy, as well as the extreme phenomena that will be explored next. Spacetime is not merely a foundation. It acts as a dynamic force interacting with matter and energy, shaping every structure and process in the universe that the naked eye cannot see. When spacetime is bent to extreme levels and phenomena such as black holes or pulsars appear, the next natural question arises: what creates this curvature? The answer does not lie solely in the ordinary matter we can see. A large portion of the gravitational force in the universe comes from dark matter, a form of invisible matter that cannot be directly observed. We only know of its existence through its gravitational influence, the orbits of galaxies, the rotation speed of galactic disks, and the way galaxy clusters interact. Dark matter not only exists, but also shapes the large-scale structure of the universe. It forms the underlying framework for filaments and superclusters, determining where ordinary matter accumulates to form galaxies and galaxy clusters. One major open question is whether primordial black holes or yet undiscovered particles make up most of dark matter. Black holes formed within the first seconds after the Big Bang may still drift through the universe, possibly even near our solar system, contributing to the invisible mass that governs the dynamics of our galaxy. Alongside dark matter is dark energy, the powerful force driving the accelerating expansion of the universe. This expansion not only causes galaxies to move away from one another, but also creates enormous cosmic voids and pushes some galaxies beyond the speed of light relative to each other, not because objects move faster than light, but because spacetime itself expands quickly enough to increase the distance between them faster than light can travel. A major open problem is the true nature of dark energy. Is it a stable cosmological constant, or a dynamic energy field that evolves over time and is not yet fully understood? The answer will determine the ultimate fate of the universe, from heat death to the Big Rip scenario, where extreme expansion tears apart every bond of matter. These mysteries are directly linked to extreme phenomena that we have already observed: hypervelocity stars escaping their galaxies, supermassive black holes such as TON 618 forming extremely rapidly, and enormous cosmic voids like the Bootes void. All of these are influenced by the invisible gravitational pull of dark matter and the expansion rate driven by dark energy, demonstrating that the universe is governed not only by objects we can see, but also by hidden components that subtly yet powerfully control everything. Dark matter and dark energy are not merely components, they are the mechanisms controlling the universe, connecting every galaxy, every supercluster, and every extreme phenomenon. Understanding them is the next step toward exploring extreme theoretical objects such as primordial black holes, quark stars, and white holes, opening the door to regions of the universe that current physics has not yet been able to describe. If dark matter and dark energy are the invisible forces controlling the entire universe, then extreme theoretical objects are living evidence of how these forces interact with space-time and matter at their limits. Imagine places where the ordinary laws of physics are pushed to their boundaries: primordial black holes, white holes, or quark stars. Stars unlike anything we have ever known, all existing at the delicate boundary between theory and reality. Primordial black holes may have formed within the first fractions of a second after the Big Bang, from regions where matter density was higher than the surrounding environment. They were not created from dying stars, but from matter compressed by its own gravity, ranging in size from something as small as an atom to millions of times the mass of the Sun. If they exist, these black holes may still drift throughout the universe, possibly even within our solar system, and could constitute part of the dark matter we observe indirectly. White holes and wormholes are other theoretical objects predicted by Einstein as the inverse counterparts of black holes. While black holes pull in matter and energy, white holes expel everything outward and allow nothing to enter. Some modern theories link them to wormholes, bridges in space-time, where matter falling into a black hole could emerge elsewhere through a white hole. However, practical use or travel through wormholes remains purely hypothetical because the internal structure of black holes is highly unstable and collapses rapidly. Some other extreme objects even challenge the definition of matter itself. Quark stars and exotic matter are predicted to form under extreme conditions between neutron stars and black holes. In such stars, quarks, the components of protons and neutrons, may exist freely or form strange quark matter, a form of matter potentially more stable than ordinary atomic nuclei. If this is true, a quark star would be smaller and denser than a neutron star of the same mass, with an extremely sharp surface and no ordinary matter mixed within it, raising the possibility of strange nuggets that could transform surrounding matter upon contact. These objects are not purely theoretical. Some extremely fast pulsars already exist, such as the Black Widow pulsar, which spins hundreds of times per second, eroding its companion star and emitting radiation pulses so precise that they can function like astronomical atomic clocks. These discoveries open the door to studying extreme physics, where gravity, density, and pressure create entirely new states of matter beyond anything that can be tested in laboratories. Extreme theoretical phenomena are not merely stories about distant objects. They demonstrate how matter, energy, and space-time interact in extreme environments. From these phenomena, scientists hope to uncover connections that explain dark matter, primordial black holes, and the large-scale cosmological events we observe. When observing the universe on extremely large scales, phenomena that once seemed isolated, such as primordial black holes or extremely fast pulsars, suddenly gain meaning within a larger cosmic picture. The universe is not completely uniform space. Instead, it contains patterns, structures, and voids that standard models cannot fully explain. These discoveries raise an important question: is the universe truly homogeneous and isotropic on all scales? Or do preferred directions and unexplained matter distributions exist? One notable example is the axis of evil, where temperature distributions in the cosmic microwave background, CMB, show large-scale fluctuations that are not entirely random but appear aligned along a specific axis. This challenges the cosmological principle, which assumes that on extremely large scales, the universe appears uniform and directionless from any observation point. Scientists continue debating whether this alignment results from our observational position or represents a real feature of the universe, reflecting conditions before or during the earliest moments after the Big Bang. At the same time, supervoids and superclusters, enormous, empty, or densely populated regions beyond predicted scales, shed light on how dark matter and dark energy govern cosmic dynamics. Supervoids, such as the Boötes void, are enormous regions where thousands of normal galaxies appear to be missing, posing direct challenges to models of cosmic structure formation. Conversely, superclusters are vast networks of galaxies connecting clusters together through filaments, stretching hundreds of millions of light-years, evidence of gravitational influence and physical processes not yet fully understood. These structures are not static. Superclusters and filaments influence the rotational direction of galaxies within their domains, producing enormous angular momentum correlations not predicted by standard models. A study of quasars suggests that their rotational axes appear aligned with surrounding cosmic structures across distances of billions of light-years, an effect that cannot be explained by any known force or interaction since the Big Bang. These observations suggest a remarkable idea on the largest scales. The universe may contain patterns and preferred directions formed within the earliest seconds after the Big Bang. These arrangements may reflect extremely early density fluctuations interacting with dark matter and dark energy to create the cosmic web of structures we observe today. Thus, when we observe supervoids, superclusters, the axis of evil, or unusual alignments, we are seeing traces of the universe's earliest formation processes. At the same time, we are reminded that extreme phenomena such as quark stars, primordial black holes, and extremely fast pulsars all operate within the same universe of immense scale and complex structure. Each discovery on this cosmic scale challenges current theory and hints at unknown forces and physics beyond galactic boundaries, paving the way for deeper scientific exploration in the future. If the universe contains enormous structures such as superclusters and filaments, then within those structures exist extreme energy sources where matter and energy operate at intensities close to nature's limits. Examples include quasars and active galactic nuclei (AGN), ultra-luminous galactic cores powered by supermassive black holes, consuming surrounding matter. As gas and matter fall into a black hole, they are compressed and heated to millions of degrees, releasing enormous energy that illuminates entire galaxies and sometimes exceeds the combined light of all stars within them. A major challenge posed by early universe quasars is that the universe appears too young for black holes to grow so massive. Some supermassive black holes reached hundreds of millions or even billions of solar masses only a few 100 million years after the Big Bang. While standard growth rates, based on the Eddington limit, cannot account for such rapid formation, this raises an open question: are new physical mechanisms involved, such as direct collapse, black holes forming from enormous gas clouds without a stellar phase, or super Eddington accretion, allowing black holes to grow faster than standard physical limits? Another extreme phenomenon, but in terms of unusual dynamics, is hypervelocity stars. These stars are ejected from galaxies by supermassive black holes such as Sagittarius A times at the center of the Milky Way at speeds of millions of miles per hour, sometimes fast enough to escape the gravitational pull of the entire galaxy. Some theories suggest these stars could even carry planets with them, and theoretically, those planets might exist in complete isolation while maintaining internal biological environments through internal energy sources, such as radioactive decay or geothermal heat. These are examples of exotic biology, where life does not depend on stellar light. These phenomena highlight that galaxies are not static structures, but enormous energy machines, where black holes, quasars, and matter ejection processes continuously interact, creating extreme environments that challenge every physical theory. These mechanisms are not only crucial for explaining galactic evolution, but are also directly connected to the formation of heavy elements such as gold, platinum, and uranium, produced in neutron star collisions or extreme quasar environments, providing the raw materials for planets and life. Understanding the extreme energy of galaxies and the role of hypervelocity stars opens deeper scientific questions. How do galaxies form supermassive black holes so quickly? Could these violent matter ejection mechanisms create environments suitable for unusual forms of life? Most importantly, they show that the universe operates through rhythms of extreme energy that we have only begun to observe and have not yet fully understood. If the universe is extreme on the scale of galaxies, with brilliant quasars and enormous black holes, then planets themselves may exist in physical and chemical states never seen on Earth. A notable example is exoplanets with extreme chemistry, such as carbon-rich planets or planets containing superionic water. These planets are not only larger than Earth, but also experience pressures and temperatures that cause water or chemical compounds to behave in entirely different ways. On some planets, water may exist in a superionic state, where oxygen forms a solid crystal lattice, while hydrogen moves freely like a liquid, creating a state of matter never naturally observed on Earth. Carbon-rich planets are another example of extreme chemistry. Their cores may contain enormous diamonds, formed under pressure that produces thick carbon layers heavier than all Earth's mineral deposits combined. These planets show that planetary chemical and physical compositions can become extraordinarily extreme, opening possibilities for non-standard habitability environments that do not depend on liquid water or Earth-like temperatures. Another example is rogue planets, planets drifting freely without orbiting any star, completely isolated in interstellar or intergalactic space. Their surface temperatures approach absolute zero, all surface liquids freeze, and they move through complete darkness. Yet some rogue planets may maintain internal heat from radioactive decay or core energy, preserving subsurface oceans for billions of years. In such cases, a starless world could still host complex chemical environments where reactions occur within liquid layers protected by thick ice shells. This represents a form of biology independent of stars, a theoretical but scientifically plausible concept. These discoveries show that the universe is not only a realm of gigantic structures, black holes, and quasars, but also an endless natural laboratory where matter and energy cycle through extreme conditions, producing planets with states of matter, chemistry, and energy that Earth science has never experienced. They remind us that survival and physical conditions are not limited by what is familiar, but are constantly revealing surprises across the universe. If planets can exist with extreme chemistry or rogue planets drifting in intergalactic darkness, then the scale of the early universe was far more violent and unimaginable. In the first seconds after the Big Bang, the universe was not completely uniform. Tiny density fluctuations existed, regions where matter was slightly denser or emptier than their surroundings. These fluctuations became the seeds for every large structure we see today: galaxies, superclusters, and the enormous voids observed across the cosmos. During this primordial era, primordial black holes may have formed from high-density regions before the universe had time to expand. They did not require the death of stars to appear. They simply collapsed under their own gravity. Their size could range from that of an atom containing the mass of a mountain to millions of times the mass of the Sun. If they exist, these primordial black holes would not only be a component of dark matter, but would also preserve traces of the conditions of the early universe, opening opportunities to study extreme events from the very first milliseconds after the Big Bang. In addition, theoretical concepts such as white holes and wormholes arise from solutions to general relativity. White holes are considered the inverse counterparts of black holes. Matter and energy are only expelled outward, and nothing can enter. In some theories, white holes may be connected to black holes through wormholes, a space-time bridge between two different locations or moments in the universe. Although the practical possibility of traveling through wormholes is almost impossible, these models remain mathematically consistent and suggest ways in which matter, energy, and information might be transported in the extreme universe. Another aspect is quark matter and quark stars, where matter reaches extreme densities between neutron stars and black holes. Quarks, the components of protons and neutrons, may exist in a free state or form strange quark matter, an extremely stable form of matter. If they exist, quark stars would be smaller and denser than neutron stars of the same mass, with sharp surfaces and no ordinary matter mixed in. These objects illuminate the limits of physics, where the usual laws of matter no longer apply, opening the possibility of states of matter that humans have never produced in the laboratory. The discoveries of these extreme objects are entirely thanks to modern observational technology, gravitational lensing, microlensing, spectroscopic analysis, along with X-ray and gamma-ray astronomy observations. Through these methods, scientists detect primordial black holes, quark stars, potential white holes, and track extremely fast pulsars and other high-energy phenomena, thereby testing new physical theories and expanding the limits of our understanding of the universe. These discoveries remind us that the universe is not merely an empty space. It is a vast experiment in which matter, energy, and space-time interact in extreme ways, forming objects and phenomena far beyond direct observation. From the primordial Big Bang to primordial black holes and quark stars, each discovery is a clue to understanding the deep structure and the still undiscovered forces of the universe. Looking back at the entire journey from gigantic black holes, extremely fast pulsars, and quark stars to supervoids and superclusters, it is clear that the universe far exceeds every human capacity for perception and prediction. A series of open questions still remain unanswered. Is the universe truly homogeneous on extremely large scales, or not gigantic voids? The axis of evil and the alignment of the rotational axes of galaxies suggest that there may be patterns and preferred directions not predicted by standard theory. Dark matter and dark energy remain the deepest mysteries. They make up nearly 95% of the total energy and matter of the universe, yet their true nature is still unknown. Could primordial black holes, unidentified particles, or even quark stars and white holes partly explain the existence of dark matter? Dark energy drives the expansion of space-time, creates the cosmic horizon and the Big Rip, and directly affects the long-term existence of all galaxies, planets, and matter. Extreme phenomena, from hypervelocity stars and quasars to magnetars and black widow pulsars, not only show that the universe operates at maximum intensity, but also open the possibility of discovering new physics. These objects challenge the limits of physical laws, where gravity, pressure, temperature, and density exceed anything that can be simulated on Earth, hinting at previously unseen states of matter such as quark matter, strange quark stars, and subaryonic water in planets. Strange planets, from carbon-rich planets and subaryonic water worlds to rogue planets, expand the possibility of studying non-standard habitability, where biology may exist without requiring starlight, relying only on internal energy or extreme chemical reactions. They demonstrate that the universe is not only extreme on the galactic scale, but also on the planetary scale. From a philosophical perspective, all of these discoveries remind us that humanity observes only a brief moment in cosmic history. The scale and intensity of these phenomena go far beyond imagination, suggesting that current physical laws may need to be revised or expanded. The universe is not merely a place where events occur. It is a gigantic natural experiment in which every force and every form of matter tests the power of our theories. This also raises a major question: could there be a multiverse, where extreme physical conditions or primordial black holes in the solar system are only a small part of a much larger structure? Could white holes or wormholes truly exist, forming bridges between different parts of space-time? And in that context, are we living in a special era of the universe, when all structures still exist and can still be observed, before the expansion of space-time erases every trace? Viewed as a whole, the intellectual challenges we face are not merely scientific questions. They open a new vision of humanity's place in the universe. We are not only observers, we are fortunate beings living in a moment when the universe is still luminous, before it moves toward a state of heat death where all matter, energy, and events ultimately dissolve into complete equilibrium. A universe of absolute silence. It is precisely in this brief span of time, while black holes, superclusters, rogue planets, and extreme phenomena still exist, that humanity can ask, where did all of this come from? And how does the universe truly work? This may be the most important question the universe has ever created, and it is still waiting for an answer. We can continue going farther still, because even after passing through the greatest questions about dark matter, dark energy, the gigantic structures of the universe, and extreme states of matter, there remains a deeper layer of questions lying in the very way we understand reality itself. For many decades, physicists have realized that even the most successful theories of modern science still contain a gap that cannot yet be crossed. General relativity describes with great precision how space-time bends under the influence of gravity, explaining the motion of galaxies, black holes, and the expansion of the universe. Meanwhile, quantum mechanics describes the world on the smallest scales, where particles exist as probabilities, where energy appears in discrete packets, and where states can be superposed. Both theories have been tested with nearly absolute precision within their own domains. But when we try to apply them simultaneously, for example, at the center of a black hole, or in the first instant of the Big Bang, they begin to conflict. The equations become infinite. Physical values lose their meaning. This suggests that a deeper theory of reality must exist, one capable of unifying gravity with the quantum world. One candidate for this unification is string theory, the hypothesis that fundamental particles are not infinitely small points, but tiny vibrating strings in a higher dimensional spacetime. In this model, the forces of nature and the different kinds of particles are simply different vibrational modes of the same basic structure. String theory even suggests that the universe may contain more spatial dimensions than the three familiar ones, but that those extra dimensions are curled up at extremely small scales. Another approach is loop quantum gravity, in which spacetime is not a smooth, continuous background, but a discrete quantum network, like an extremely fine mesh. In this view, spacetime itself may be built from the smallest units, and singularities such as those inside black holes may not actually be infinite, but merely places where the quantum structure of spacetime becomes extreme. These theories are still under development and have not yet received direct experimental confirmation, but they open the possibility that spacetime, matter, and energy may simply be different manifestations of the same deeper structure of the universe. Alongside the development of theory, observational technology is also advancing very rapidly. New generation telescopes such as the James Webb Space Telescope, gravitational wave observatories such as LIGO and Virgo, and large-scale cosmic mapping projects are providing data unlike anything seen before. Thanks to these tools, we can see galaxies forming only a few 100 million years after the Big Bang, detect black hole mergers billions of light years away, and trace cosmic structures on enormous scales. These observations are gradually revealing that the universe may be far more complex than the original simple model suggested. Galaxies appear earlier than predicted. Some supermassive black holes form too quickly. Cosmic structures may be larger than theoretical limits allow. And in the ancient microwave background radiation of the universe, small anomalies are still causing scientists to debate. This is not a sign that science has failed. On the contrary, it is a sign that we are standing at the boundary of new discovery. Every time the universe does not fully match the current model, that is precisely where science takes a major step forward. Perhaps in the future, we will discover the true nature of dark matter. Perhaps we will understand what dark energy is. Perhaps we will find a way to unify gravity and quantum theory. Or even discover that our universe is only part of a much larger structure, a multiverse. But even if all of those questions are answered, one thing will remain unchanged. The universe we are observing is only a very small slice of its immense timeline. We exist in a special era, a time when stars are still burning, galaxies are still forming, and light from remote regions of the universe still has enough time to reach us. In the very distant future, as the universe continues to expand, most of the galaxies we see today will disappear from view. Civilizations that may exist then could look up at the sky and see only a solitary galaxy amid darkness, never knowing that the universe was once so vast and full of structure. That means we are living in a rare moment in cosmic history, when the greatest questions can still be asked and may still be answered. And perhaps the most astonishing thing is not the size of the universe, nor the extreme phenomena it contains. It is that, in a small corner of an ordinary galaxy, on a rocky planet orbiting an average star, The universe has created beings capable of looking up at the sky and trying to understand its own origin. But even if we understand the origin of the universe, understand how galaxies form, and understand the nature of dark matter and dark energy, there is still a deeper question behind all of that. That question is not only how the universe works, but why it exists in this way. The laws of physics that we know, from the gravitational constant and electromagnetism to the nuclear forces, seem to be fine-tuned in a strange way. If the values of these constants were changed even slightly, the universe might have been completely different. Stars might never have formed, atoms might not have been stable, and complex structures such as planets or biology might never have appeared. This phenomenon is called the fine-tuning problem of the universe. Some scientists argue that this is simply the result of chance among countless possibilities. We just happen to live in a universe whose conditions are suitable for the existence of complex structure. But some other hypotheses go further. If a multiverse exists, a vast collection of universes with different physical laws, then our appearance in a suitable universe might not be special at all. In the model of eternal inflation, our universe may be only one bubble in a much larger cosmic ocean, where other bubbles continuously form with different physical constants. Some universes may collapse immediately, some may expand too quickly to form galaxies, and a few rare ones may be stable enough to create stars, planets, and eventually biology. If this is true, then the universe we observe is only one among countless possible realities. But there is still an even deeper layer of questions. Even if there are countless universes, the fundamental laws that allow their existence must still come from somewhere. The equations describing space-time, quantum fields, and the structure of matter must still have an origin. Some physicists have begun to raise a bold possibility. Perhaps the laws of physics are not the final foundation of reality. Instead, they may be consequences of a deeper structure, a basic mathematical or informational principle. One line of research that is gaining momentum is the idea that the universe may be described as an information system. In this view, matter, energy, and even space-time may be manifestations of information encoded in the basic structure of reality. Some theories related to the holographic principle even suggest that all the information in a region of space may be encoded on its boundary, like a three-dimensional image generated from a two-dimensional surface. If true, that would mean that the deepest reality of the universe may not be matter, but the structure of information and mathematics. These ideas still lie at the frontier of theoretical physics. They have not yet been verified, and it may take many decades or even centuries to test them. But they show that the journey of discovering the universe is nowhere near its end. In fact, we may only be at the beginning, because every time we expand our perspective from planets to star systems, from galaxies to galaxy clusters, from the observable universe to the possibility of a multiverse, we realize that what we know is only a very small part of a much larger picture. Perhaps in the future, more advanced civilizations will understand the true nature of space-time. Perhaps they will find ways to manipulate gravity, travel between stars, or even discover hidden dimensions that current physics has only begun to predict. But even if all of that happens, one truth will not change. The universe we live in is a vast, complex, and mysterious system, where each answer usually leads to many more questions. And perhaps that is the most astonishing thing of all. Not that the universe is enormous in size, not that it contains black holes, superstructures, or strange planets, but that within that universe there exist beings capable of asking about it, beings that can look up at the night sky, realize that those tiny points of light are distant stars, and begin asking questions about the origin of everything. And in that moment, the universe is no longer just a collection of matter and energy. It becomes a story in the process of being discovered, a story of which we have only read the first few pages. But if we look more deeply into what science is revealing, there is one aspect of the universe that human beings rarely confront directly. It is not only its vastness, not only its unimaginable distances, but something far more terrifying. The universe does not care about our existence. The laws of physics operate coldly and precisely, with no purpose, no intention, and no preference. The same forces that created galaxies are also the forces that can destroy them. The same processes that created the atoms in our bodies are also the processes that can tear them apart on a cosmic scale. Consider what is happening right now on scales invisible to the naked eye. At the centers of galaxies, supermassive black holes are devouring gas, stars, and even entire planetary systems. Elsewhere, magnetars, neutron stars, with the strongest magnetic fields in the universe, can tear apart the atomic structure of matter if you stand close enough. A magnetar at a distance equal to half the distance from Earth to the Moon could destroy every electronic device on our planet through its magnetic field alone. Meanwhile, throughout the universe, gamma-ray bursts occur when massive stars collapse or when two neutron stars collide. In just a few seconds, they release more energy than the Sun will emit over its entire lifetime. If a gamma-ray burst were aimed directly at Earth from a distance of a few thousand light-years, it could destroy the ozone layer and trigger a global extinction. And those are only the phenomena we already understand. There are even greater forces at work on cosmic scales. Dark energy is stretching space-time, pulling galaxies farther and farther apart. Over time, this expansion will cause galaxies to move beyond one another's observable range. One day, in the distant future, if other civilizations still exist in their own galaxies, they may look up at the sky and see no other galaxies at all. For them, the universe will be only a solitary galaxy in the dark. But perhaps the most terrifying thing is not these forces themselves, but the timescale on which they operate. Civilizations exist for a few thousand years. Species survive for a few million years. But cosmic processes unfold over billions, trillions, and even quadrillions of years. Over such spans, stars will burn through their fuel, galaxies will collide and merge, black holes will slowly consume what remains, and in the end, even black holes do not last forever. According to quantum mechanics, black holes gradually evaporate through Hawking radiation. A black hole with the mass of the Sun would take about 10671067 years to disappear completely. Supermassive black holes will survive much longer, but even they cannot last forever. After the last black hole evaporates, the universe will enter a stage that physics calls heat death, the thermal death of the universe. No more stars, no more galaxies, no more concentrated sources of energy, only lonely particles drifting through an almost infinite space, where the temperature approaches absolute zero and no physical process remains powerful enough to create new structures. A completely silent universe. What is terrifying here is not destruction. Destruction is an event. It has a moment of beginning and a moment of ending. What is terrifying is the absolute silence that lasts forever. No stars rising again, no galaxies forming, no living beings existing to observe. A universe where nothing happens anymore. And if we look at the entire history of the universe, from the Big Bang to heat death, one thing becomes astonishingly clear. The span of time during which stars exist, galaxies form, and life can appear, the span during which the universe can be observed is only an incredibly brief moment in its entire timeline. We are living in that rare moment. A moment when the universe still has light, when stars are still burning, when galaxies are still moving. A moment when a tiny species on a rocky planet can look up at the sky and try to understand all of this. And perhaps that is the most terrifying part of the whole story. Because if the universe is truly as immense, cold, and endless as the laws of physics suggest, then perhaps we are not the only ones looking up and asking questions. If we step back and look at everything we have explored, the violent birth of stars, the invisible pull of dark matter, the expansion of space itself, we begin to realize that the universe is not just vast. It is filled with places so extreme that they redefine what we mean by danger, destruction, and the limits of physical reality. These are not merely distant locations on a map of the cosmos. They are environments where the laws of physics push matter and energy to their absolute limits. The most terrifying places in the universe exist not because the cosmos is hostile in a deliberate sense, but because the fundamental rules of nature allow conditions that can become unimaginably extreme. Gravity, radiation, magnetic fields, density, and energy can combine in ways that create regions where survival, to structure, and even the concept of matter itself begin to break down. Consider the environment around a black hole. At a safe distance, a black hole behaves like any other massive object, influencing nearby stars through gravity. But approach the event horizon, and space and time themselves begin to warp. Gravity becomes so strong that time slows dramatically compared to distant observers. Cross the event horizon, and there is no return, no signal, no light, no information escapes. Closer still, tidal forces stretch matter into long strands in a process known as spaghettification. A star wandering too close can be torn apart, its material spiraling inward and heating to millions of degrees, creating brilliant flashes of radiation visible across entire galaxies. These events, called tidal disruption events, are some of the most violent displays in the cosmos. Yet black holes are only the beginning. Elsewhere in the universe exist magnetars, a rare type of neutron star whose magnetic fields are the strongest known in nature, trillions of times stronger than Earth's. These magnetic fields are so powerful that they distort the very structure of atoms. If a magnetar were located halfway between Earth and the Moon, its magnetic field could erase every credit card on the planet and tear apart molecular bonds in living tissue. Then there are gamma-ray bursts, brief explosions that release more energy in seconds than our sun will emit in its entire lifetime. These bursts are thought to occur when massive stars collapse into black holes or when neutron stars collide. The resulting beam of radiation travels through space like a cosmic blowtorch. If such a beam were directed toward Earth from within our own galaxy, it could strip away the atmosphere's protective ozone layer and trigger global extinction. But some of the most frightening places are terrifying not because of explosions, but because of their sheer emptiness. There are enormous regions of space called cosmic voids, where galaxies are incredibly sparse. One of the most famous, the Boötes void, spans hundreds of millions of light-years, yet contains far fewer galaxies than expected. Inside such regions, distances between galaxies stretch to unimaginable scales. A civilization living in one of these voids might look into the night sky and see almost nothing, no nearby galaxies. No bright clusters, only darkness punctuated by a few distant lights. Yet perhaps the strangest and most unsettling locations are not places we can see at all. They are hidden in the mathematics of physics itself. Theoretical objects, like white holes, the time-reversed counterparts of black holes, could theoretically expel matter instead of swallowing it. Wormholes, if they exist, might connect distant regions of space-time through shortcuts beyond normal space. These ideas remain unconfirmed, but the equations of general relativity allow them, reminding us that the universe may contain structures we have not yet learned how to detect. And beyond all of these terrifying environments lies something even more unsettling: the cosmic scale of time. Many of the most extreme places in the universe are temporary. Stars explode, neutron stars collide, black holes merge, but over trillions of years the universe itself will change in ways far more profound. Galaxies will drift apart, stars will burn out, black holes will slowly evaporate through Hawking radiation. Eventually, the cosmos may approach a state where no new structures can form, where energy is spread evenly through space and nothing meaningful can happen. This distant future, known as heat death, represents the quietest and most absolute ending imaginable, not a dramatic explosion, but the gradual fading of all activity. In that sense, the most terrifying places in the universe are not terrifying because they are malevolent. They are terrifying because they reveal the true scale of reality. They show us that the universe is capable of creating environments so extreme that matter breaks, time bends, and entire stars can be erased in moments. And yet, at the same time, those very processes are the reason we exist at all. The elements in our bodies were forged in stellar explosions. The galaxies that host stars formed through the invisible scaffolding of dark matter. The same gravitational forces that create black holes also allow planets to orbit stars and give life a stable home. The universe is both terrifying and creative in the same breath. And perhaps the most astonishing fact of all is that, In a cosmos filled with such violent and mysterious places, there exists at least one small world where conscious beings can observe it, study it, and ask why it all exists in the first place. When we look back across the entire journey from the birth of the universe to its possible endings, from black holes and magnetars to rogue planets drifting through endless darkness, one truth becomes clear. The most terrifying places in the universe are not terrifying simply because they are violent or extreme. They are terrifying because they reveal how vast, powerful, and indifferent the cosmos truly is. The same laws of physics that allow stars to shine also allow stars to collapse. The same gravity that holds planets in orbit can tear entire galaxies apart. The same universe that created life also contains places where matter itself cannot survive. Yet these terrifying places also tell a deeper story. They are the laboratories where the universe tests its own limits. In supernova explosions, the elements of life are forged. In the collisions of neutron stars, gold and heavy metals are born. In the gravity wells of black holes, space and time reveal secrets that may one day help us understand the deepest structure of reality. Every terrifying region of the cosmos, every black hole, every gamma-ray burst, every cosmic void exists because of the same fundamental forces that built the galaxies, stars, and planets we know. In other words, the terrifying universe is the same universe that made us possible. And that realization changes how we see everything. Because when we stand on Earth and look up at the night sky, we are not just looking at distant lights. We are looking into a universe filled with unimaginable extremes, places where time slows, matter collapses, and entire stars disappear. But we are also witnessing something extraordinary, a universe capable of producing observers, cheese, on a small planet, orbiting a completely ordinary star. In the outer arm of a quiet galaxy, consciousness emerged. A species evolved that could look into the darkness, measure the light of distant galaxies, decode the signals of pulsars, and ask questions about the origin of everything. The universe is vast. It is dangerous. It is filled with terrifying places. But perhaps the most astonishing fact of all is this. In a cosmos capable of creating such terrifying extremes, it also created minds capable of understanding them. And as long as we keep looking up, asking questions, and exploring the unknown, the story of the universe and our place within it is still being written.